Hi everyone, and welcome to lecture 4 of the Reliable and Interpretable Artificial Intelligence course taught at ETH Zurich. My name is Martin Vecev and I'm a professor at ETH. And this lecture 4 is going to be about adversarial defenses or mechanisms, algorithms, which we can use to produce networks and models that are less susceptible to adversarial attacks. So they are more robust to finding adversarial examples. Now, if you recall, in the last couple of lectures, we looked at adversarial examples in various settings: audio, images, natural language processing, and we studied algorithms using which we can actually find these adversarial examples called adversarial attacks. So different algorithms like FGSM, fast gradient sign method, iterative version of FGSM, targeted, untargeted, Kalinian and Wagner in both settings, audio and images, where we show the different loss formulations and the projected gradient descent, PGD attack, which we promise to be used later when we study adversarial defenses. So this lecture is a natural continuation of the adversarial attacks material. If you don't remember some of the attacks, you can just go back and watch that lecture again to refresh yourself. All right, so today we're going to be concerned ourselves with answering the following question. The question is going to be, can we avoid adversarial examples, right, altogether if possible? So many works have tried to do that, to come up with different adversarial defenses. So typically what happens is there is an adversarial defense, somebody comes up with, and then shortly after there is an adversarial attack that somebody also comes up with, and that breaks the defense. Now, some of the more experimentally successful defenses, however, in practice, tend to work by incorporating the adversarial examples during training. So they not just train on the standard training dataset, the standard label training dataset, but they also include newly generated adversarial examples in that process, on more data, if you like. Okay, now these defenses, these experimental defenses, they're more difficult to break, so it's harder to find adversarial examples. Very difficult to find, can be very difficult. So we're going to take a look at some of them, and later in the course we're going to be studying certified defenses, where it is probably impossible that one can actually find an adversarial example altogether. Now, before we study these adversarial defenses and before we see the formulation, let's look at a couple of metrics here. So let me just highlight. All right. So we're specifically going to be looking at this metric called adversarial accuracy. And adversarial accuracy refers to a metric on the data set where it's computed by taking some data point, and checking if the model, if the neural network classifies the point correctly. So the point has to it has to predict the right label for this point, and it also has to be the case that the network is robust, the model is robust around that point in the region, in the space around this point that we have designated, right? So both of these, right, we would be interested whether the point is correct and classified correctly, and whether the network is robust in a region around the point. Okay. So, all right, let's look at an example here. We're specifically going to be looking at the L infinity norm, because so far we mostly focus on the L infinity just for illustrative purposes. But this metric, you can apply it for any perturbation that you care about, presentations or audio or natural language, wherever you have, where you're able to define robustness. Okay, in the L infinity setting, let's take an epsilon, let's take a radius of 0.3, and let's assume the test set T contains 100 examples. Now, what we're going to do for each of the examples, we're going to try each of these example DI. We're going to try to find an adversarial example in the region around DI. So some other point which classifies differently than DI, right? And the way we typically do that in this setting is by using the PGD attack. You can also use another attack, but let's stick to the PGD here for our example. Okay. Now let's suppose that 95 of these 100 examples, right, classify correctly. So they classify, the neural network classifies them to the correct label that they have in the data set. So we would have an accuracy, would have a natural accuracy or test accuracy of 95%, right? Now let's suppose out of this 95, 15 of them are, for 15 of these, we are able to find an adversarial example, right? So somewhere in the region around this point, there is, of these 15 examples in the region, corresponding regions, we are able to find the point where, which classifies differently than the original point. So we'd have to subtract this 15 from the 95, and so we would end up with 80 points in the test set that are classified correctly by the model, and which are robust in the region around these points. So at least experimentally hard to find an adversarial attack. And so we would end up with adversarial accuracy of 80%. Sometimes in certain papers, some people don't have the requirement that the network classifies the point correctly. They just say, just care about robustness. But then you'd have the situation where you can make the network very robust by classifying everything to the wrong label, but it would be completely inaccurate. Anyway, this is the definition of adversarial accuracy that you most typically see in the literature. Now, one interesting point here is that this adversarial accuracy, right, and the test accuracy, the natural accuracy, tend to be at odds. Okay, they tend to be a little bit in conflict here. So you can actually end up in a situation where you are going to, you have some model with some test accuracy. Like here we have 95% and we have adversarial accuracy of 80%, but it is possible to end up in a situation when you perform adversarial training that we're going to see in the next few minutes, where the test accuracy drops. So maybe the test accuracy reduces from 95 to 90%, let's say in our example. And however, the adversarial accuracy can increase. So the adversarial accuracy maybe goes up to 82%, right? So you have less points classifying correctly, but more points are actually robust. And so what happens is, so this trade-off here, right, of accuracy versus adversarial accuracy and test accuracy, why it happens, it's still a very active research question, and obtaining networks and models that have state-of-the-art test accuracy, natural accuracy, and adversarial accuracy is still a challenging problem. So let's clear this so we are not interrupted by the drawings, and let's look at one of the more popular adversarial defenses that tends to get used in practice. Okay, so probably it's not surprising to you that the adversarial defense is going to be phrased as an optimization problem. So let's move this thing here so we don't get bothered by this. Okay. Now, let's dissect this a little bit. What is happening here? All right. So what we see first of all here is we have a nested optimization problem. So this is an adversarial defense formulation of an adversarial defense, which has to solve the following big optimization problem. So we have minimization, outer minimization, and we have inner maximization here. So we have a min-max optimization problem, which are, these optimization problems are difficult to solve. not surprisingly. So what this thing says here is we want to find parameters theta. So you can think of them as the weights of the neural network, okay, which minimizes this function, okay, minimizes this function here. And what this function is the expected value of this function over here, okay, with respect to the underlying distribution D, all right? Okay, so let's dissect this. So what this says here, this what I've underlined in green, all right? What this Max says here is Max says, let's think of it this way. Let's pick a point, okay, X over here, and we have some region around X, some S of X. This may be the L infinity ball around X that we looked at before. And let's find a point in that region with X prime, which maximizes the loss that we are going to be using for training. Okay, could be, for instance, the cross entropy loss or some other loss that you want to use here. Okay, so the goal of this inner maximization problem is to find an X prime, try to find the point which in that region around X, which maximizes the loss. So tries to achieve, let's say, worst case behavior, if you want. So intuitively, what you can think of it this way, that you want to find the worst case behavior, okay, here in the max, and then you want to minimize the effect of this worst case situation. Okay, so you're trying to find data that minimizes this worst case situation, this worst case finding that you discovered here in the maximization. You try to find the worst case situation, and then you try to fight against this worst case situation by minimizing its effect, if you want. Okay, so that's all there is here in this nested optimization problem, referred to as an adversarial experimental adversarial defense. It was introduced in Madri and co-author papers in 2017. So that's a popular formulation that tends to work as good as quite good in practice. Okay, so this is the optimization problem. One point to make here is that we're going to be seeing such optimization problems several times in the future. So that's why it's important to understand this also. We're going to be seeing when we're talking about incorporation of background priors, because really what we're doing here, I'm just prefetching a little bit, but just to give you a bit of context, is that we're really training here the neural network with respect to a given property, robustness, right? We're trying to enforce this property of robustness. You may have other properties that you express in some logic, some specification, and we're going to see this later. And we're again going to see this min-max kind of formulation. We're also going to be seeing it when we're talking about certified defenses. Again, similar min-max formulation. Okay. Here is another point, just to connect this to standard training. So let me just erase these drawings here, and let's use like right here. I don't know if we can use a. Maybe let's experiment a bit with the colors. So if I do the following thing and I erase this max here, let's say that I remove the max, okay? Then I delete this thing over here, okay? And I replace this X prime over here. I get rid of this and I replace it with X. Okay, let's use text here. Okay, so if I put X over here, okay, if I put X instead of X prime, so I'm deleting this max situation. Okay, I'm removing it. So I'm just removing this stuff, deleting it. Then what am I going to end up with? So I essentially have the expected value, the expectation of the loss function, right here. So I just end up with standard training. Okay, this is the standard, pretty much the standard machine learning training. Okay, so this just augments the standard machine learning training by, instead of training on the underlying distribution here, the line distribution here D, which is approximated, oscillator is approximated a standard with the given label data set. We are training with this adversarial examples and the max formulation. So this is how from the normal, from the standard adversarial training, you can end up the normal machine learning training problem. Okay, so this is just a point. So let's move on here. So I hope that this makes sense. Let's see. And then yes, of course, over here at the bottom, I have, oopsie, over here at the bottom, this S of X denotes the region around which we care to make the model robust. So this perturbation region can be, again, whatever it is that you are, whatever region you're interested in. In our case, we have shown the example below here with the M infinity ball, right? But you can also work with other regions. All right, so let's see how we solve this min-max optimization problem in practice, which can be, it's interesting. So here's the way that typically gets implemented in practice. So let's again use our notations here. So it's going to be in several steps. So first, we're going to select a mini batch of examples from the data set, from the label data set that we're given, right? That comes from the underlying distribution. Okay, and so we're given the standard data set D, and then what we're going to do, we're going to compute this set. Think of it this way: we're computing this set B max, okay, and the B max is computed from B. And the way that it's computed from B is that for every point in B, for every point that we have in this mini batch, we are going to be applying the PGD attack. This is the attack that we looked at in the previous lectures, in the last lecture 3. And so what's going to happen here is we are going to try to find, over here, we're going to try to find and value X max, okay, like with PGD, that maximizes the loss, okay, the loss function over here. All right, and so as we mentioned earlier, if you remember in the lecture 3, this, when it's used in the case of adversarial defenses like we are doing here, PGD is used in that setting, then the resulting point need not be an adversarial example. It is just a point where hopefully the loss is maximized. So that's what happens here. So then we accumulate, a bunch of these X maxes with the corresponding Y's in this the labels in the set B max. Okay, right. So the size of B max is going to be the same size as the size of the set B. Okay, once we have accumulated the set B max, so what we have done in a sense here, we have linearized the inner maximization problem. We have computed some approximate solution to this problem, and we got rid of this problem. And now that we have the B max, we can just do the standard gradient step over here. This is a standard gradient step, except that this time we are working with the set B max instead of the set B. Okay, so this is the standard gradient step that we do in training. Okay, one interesting point here that you can take a look later. It's not something that we're going to be studying, how to derive this gradient here to be pushed next, to go here, to how to obtain this derivation here. You can look at from the original min-max problem, you can look at that's theorem, and it can be quickly derived how you go from the min-max to this to the gradient being pushed inside here of the loss. Okay, so this is the implementation of the PGD defense in practice. So we obtain the new weights, take the gradient step, and we continue back and do the standard training, but just this time with this Bmax instead of B. Okay, so this is the implementation of the PGD defense in practice. So as you see here, a lot depends on how good your PGD attack is. That's what we looked at last time. So all these projections and right, how quickly you can find the point, and this X max. So one interesting point here is, and I'm going to mention it again with the projection, like look at we are invoking the PGD attacks during training. So we build this at Bmax, and then we update the weights here. Because this is done in this iterative manner during training, and this PGD attack may be invoked many times on all the points that we're interested in during training, it has to be fast. So if your projections are very slow, it actually may be not so feasible to train with, to apply these adversarial defenses like PGD defenses in practice. So this is also why fast projections are important, because we are using these projections during attacks and consequently during training here very often and very frequently. Okay, so let's move on from here. From that, you got an idea what the PGD defense is. This is experimentally one of the more successful defenses. It's really a baseline when you are training adversarial models to train with this PGD defense. Okay, so let's see. There's a little bit of discussion in the original Madrid paper on why this is these various questions. One of them is why we can find good approximate solutions to this inner maximization problem. Why do we think we can approximate it well? And so they did a bunch of experiments, and so basically what this experiment shows that there are many local maxima that are inside this region, let's say this infinity ball around X, have quite concentrated loss values. Okay, so there are many, if you want, good points which you can train, which is in line why potentially some hypothesis why neural network training works altogether. There are many good points that perform well. Okay, now this graph over here, so the way that this graph is produced is you can pick a single example just to illustrate this point above. You can just pick a single example in the data set X, let's say. And what you want to do is you want to plot the values of the loss function of 100,000 starting points around X. So basically you pick X, you have the region SX around X, and then you have 100,000 random starts. And for each of these, you can try to maximize using PGD, you can try to maximize the value of the loss, and then you can plot that value. All right. And so here in red, what we see here is the values of this loss for these examples on a network which is adversarially trained, however. So it's already trained with this PGD defense, with this adversarial defense. And what you see here is that the values of the loss are fairly concentrated, which is hopefully what you would expect. And they are small, so they're not just concentrated around a particular value, which is 0 here, but they're small. The value of the loss is small. Okay. If you plot the same graph, perform the same experiment, and you plot the corresponding graph on a not adversarial trained network where PGD defense has not been applied, you'd get a bit of a different distribution. All right, it would look something like this. Okay, so the values of the loss function would be much higher, and it would be more scattered here around 100, I guess. Okay, so much greater variance here that we see. Okay, of course, this experiment, can be elaborated on more, and one can do more experiments because this is an untrained network, right? This is undefended network, the blue one, and the red one is for a defended network already. Okay, so you can try to, plot this, produce such plots during training and see what happens during training. Maybe you are slowly and slowly going from the, the blue to the red over here. And so ultimately what it tries to show that is that there are many good values of the loss, right? And they're fairly concentrated. So hopefully you can find them easier. Okay, but a lot more can be studied here as well in this hypothesis. All right. There was another question, that some additional points that I wanted to mention, that also the original paper mentions, right, from 2017, and there's been many works that have elaborated on these points. So obviously model capacity matters, right? As we mentioned, even I think in the second lecture, the larger the network it is, the more easily it can fit the decision boundary. So it's harder to attack. Okay. So if you have very small nets, it just may be hard to fit this more complex decision boundaries around this region that you care about, the region that you care to train the network to be robust. Now, training with multiple iterations of the FGSM, like this PGD with projection, which is FGSM, iterative FGSM essentially with projection, right? With tends to perform better than training with one step, which is probably not surprising. You're able to find greater values of the loss. Okay, maximize the loss more successfully. Now, of course, even with this, the problem is that even with these adversarial defenses, right now what we're seeing is state-of-the-art defenses pretty much still affect the negatively affect the accuracy. So the natural accuracy, the standard accuracy goes down, and although you get much better adversarial accuracy. And there's various papers that are studying this phenomenon, right? That I encourage you to take a look. There's been many follow-ups of these works, this relationship between adversarial and natural accuracy, right? This paper over here at the bottom, that introduces a defense code traits. What it tries to do is it tries to give you a principled way for deriving the optimization problem, right? And what it does, so there's two parts, how to theoretically justify that, the corresponding min-max optimization problem. They derive a slightly different problem than the one we showed, than the standard adversarial defense. And that derivation includes a mixture of this adversarial loss, if you like, with the standard loss. And they perform various experiments. There's been, the corresponding defenses called traits. In practice, what we see is that really there isn't much difference between this traits defense, which actually won the 2018 NeurIPS adversarial challenge, and the PGD defense. So in our experiments on different data sets, it is actually quite not difficult to use PGD defense to reach the same numbers as the traits defense. But still, I think it is interesting for its for the how to derive these loss terms in a principled manner. So I encourage you to take a look at this. Okay. One thing else I wanted to mention to you before we wrap up with these adversarial defenses is this work that we did with one of the graduate students in the lab, Pavel Bielik, and the link is here for the slides, the talk, and the video talk and the paper. And what's interesting about this work, which is why I encourage you to read it, not just because we did this work, but because it's actually, there are several reasons. It's not something that we're going to be examining, but it's just something useful for your education, is that it involves a bunch of components together that you actually don't often see when you're working only in the domain of vision, like robust visual perception, images. So what it does is it involves PGD training, the adversarial training. You see this min-max formulation there, just like we just saw in the lecture, which is quite nice. So you see it in a different setting, which is the building robust machine learning models of code. So if you have lots of programs in the world, you want to learn a model, just like you want to learn a model over natural language. Here, you just want to learn a model over programs. Okay, so it's semantically a much richer setting. So you'll see there this adversarial training, how it's used, pretty much the same as we outlined today. But you also see another ingredient, which is about learning representations, right? Over what it is that your model works on. So this is actually an ingredient we haven't looked at, but it's quite interesting. And there is also abstention learning when not to make predictions when you're not confident. Okay, so these three ingredients, which by themselves you can see separately in different papers, are somehow put together in the setting of adversarial models of code, right? And that's why I think it's actually quite a nice instructive paper to read. Moreover, the area is actually fairly unexplored, right? There isn't much work in this space, and so the work we did is fairly recent, and I'm sure that many of you can actually improve on it substantially by looking in many different tasks codes and potentially different ways to perform the adversarial training with different parameters, different representations, and so on. So it's both an instructive and an interesting area to explore in the future. Okay, so this was a fairly short lecture because we already outlined the prerequisites and the some of the underlying algorithms, like the adversarial attacks, PGD attacks, and we explained them in the earlier lectures, and now we just putting it all together in this min-max optimization problem. So what we saw here is how to define an optimization problem so that we can, this min-max optimization problem, so that we can perform an adversarial training and define these adversarial defenses. And ultimately it comes down to training with adversarial examples. Those have been the most robust, the most experimentally successful defenses. Specifically, the PGD defense, which you see as a baseline in pretty much any paper that works in this space. Right? We showed the min-max optimization problem, and we showed how to linearize the inner maximization problem by using the PGD attack to find these points that maximize the loss, and then performing standard training on those generated points. One interesting point here is that adversarial training can lower standard accuracy, can lower the natural accuracy. And so there is much interesting research that remains to be done here, to where we can reach models with both high standard accuracy and high adversarial accuracy for different application domains, ranging from code to natural language to audio processing, image processing, video processing, and so on. So that's a very active area of research, and hopefully these last few lectures give you a little bit of an introduction in this space. And I mentioned at the end one interesting new area that seems to be rather unexplored and starting now, a new domain, which is the domain of learning from millions of problems. So I hope you found the lecture interesting and useful, and I will see you next time.